Hi students, in this video we are going to study about spectral lines of hydrogen atom. Now in the previous video we discussed about the energy levels of hydrogen atom. Means each orbit is having, the electrons in each orbit possess a definite amount of energy. Now if the atom is provided with some external source of energy like temperature, heat, electric field or electron collision, what happens is that the electrons, the orbits, they gain this energy and they jump into the higher level, that is what we call the excited level. From the ground state they may jump into the higher level, but since they possess the extra amount of energy, they will be highly unstable, and due to this instability what happens is that this electron gives the energy out in the form of photons or light, and they will come back to the either to the initial state or to the initial level or to the intermediate level. And the person who observes this using the spectroscopic instruments will be able to see certain lines which we call the spectral lines. And Sir Bohr was credited with his contribution of explaining the spectral lines of hydrogen atom with the Nobel Prize in 1922. So first let us see how these spectral lines are formed and what are the names given to the set of spectral lines. We have studied that the energy of the electron in the nth orbit of an hydrogen atom is given by En is equal to minus 2 pi square mk square z square e raised to 4 divided by n square h square. Now in the case of hydrogen atom we know the value of z is 1, and also imagine an electron making its transition from energy level En2 to level En1. So from one level, from a higher level, it is coming back to the ground state level En2 to En1. Okay. Now according to Bohr's frequency condition, Bohr told that when an electron jumps, an electron can jump from a higher level to a lower level or vice versa by emitting a photon having a frequency nu. So what happens when electron jumps from En2 to En1, the difference of energy is given by the equation h nu, which is equal to, using this above equation we can write is equal to minus 2 pi square mk square, is it the value of z is 1, so leave it, e raised to 4 divided by h square, all these are common, isn't it, into minus 1 by n2 square minus 1 by n1 square. Now I am going to bring this h to this side, so we will get nu is equal to minus 2 pi square mk square e raised to 4 divided by h cube into, on rearranging, minus of minus is plus, so 1 by n1 square minus 1 by n2 square. So then what the next step is, we know the relation between frequency, speed of light and wavelength as the relation between frequency, speed of light and wavelength is given by the equation C is equal to nu lambda. Instead of V we are using C, or we can write nu is equal to C divided by lambda. Substituting the value of nu in the above equation we get C by lambda is equal to minus 2 pi square mk square e raised to 4 divided by h cube into 1 by n1 square minus 1 by n2 square. Now I am going to bring this C to the denominator, so I will get the equation as 1 by lambda is equal to minus 2 pi square mk square e raised to 4 divided by c h cube into 1 by n1 square minus 1 by n2 Now we have studied what is 1 by lambda last year. 1 by lambda is known by the name wave number. Represented using by nu bar, and also 2 pi square, and also 2 pi square mk square e raised to 4 by ch cube is also constant. So it is known by the name R, where R is known as Rydberg's constant, having the value of 1.03 into 10 raised to 7 meter raised to minus 1. So we can write this R is equal to minus 2 pi square mk square e raised to 4 divided by ch cube. The value is 1.03 into 10 raised to 7 meter raised to minus 1, known by the name Rydberg constant. So our final equation for the difference in energy is, for in terms of wave number, is nu bar is equal to R into 1 by n1 square minus 1 by n2 square. Using this equation, we can explain the formation of several spectral lines. Now, in the previous videos, we saw energy levels is represented by certain parallel horizontal lines. N is equal to 1, N is equal to 2, equal to 3, N is equal to 4, etc. Now, if the electron from higher energy state, that is the excited state, jumps to the ground state, then it forms a series of lines known by the name Lyman series. Similarly, if the excited electrons from higher state jumps to the second energy state, then it is known by the name Balmer series, etc., etc. So let us study which are these set of lines, spectral lines, or the light emitted is known by the name Lyman series. Similarly, this set of lines is known by name Balmer series, etc., etc. So next we are going to study about the series of spectral lines. First one, we have the Lyman series. That is, when an excited electron jumps from the higher energy level to the ground state, that is the lowest energy level, we get the Lyman series. This series lies in the UV region. The light comes out as UV light, and the equation is nu bar is equal to R into from the higher state to the ground state. So R is equal to 1 by 1 square minus 1 by n2 square, where n2 can be any value 2, 3, 4, etc. Similarly, next we have the Balmer series, in which if the electron is jumping from higher energy level to the second level energy level, then this series will be seen as visible light, and we obtain the equation as nu bar is equal to R into 1 by 2 square minus 1 by n2 square, where n2 is equal to 3, 4, 5, etc. Similarly, if an electron jumps from the from higher levels to the third level, then we have the Paschen series, and the equation for it is nu bar is equal to R into 1 by 3 square minus 1 by n2 square, where n2 is 4, 5, 6, etc. Next we have the bracket series. All these are named after the persons who found it. And this series here, n1 will be is equal to 4, which means excited electrons in the higher level will jump to the fourth state, where and n2 will be 5, 6, 7, etc. And this series lies in the far infrared region. So nu bar is equal to 1 by R into 1 by 4 square minus 1 by n2 square. And finally we have the Phy12 series, in which n1 is 5 and n2 is 6, 7, 8, and this series lies in the very far infrared region. So using these equations, Balmer obtained the spectral series of hydrogen atom like this. If the electron is getting excited to higher energy level, and if it is jumping from the higher energy level to the ground state. From any of the higher energy level to the ground state, we can obtain the Lyman series. Now, if electron is jumping from the higher excited state to n is equal to 2 state or n is equal to 2 level, energy level, we have the Balmer series. And if from higher energy state, if the excited electron is jumping to the n is equal to 3 state or third level, we have the Paschen series. Or we have, if it is jumping from the higher states to the fourth state, then we have the bracket, and finally we have the Phy12 series if the excited electron is jumping from higher energy state to the n is equal to 5th level. Now, this is the spectral line of a hydrogen atom when the excited electron jumps from a higher level to the ground state or corresponding other initial intermediate states. Okay. Thank you.